to understand the concept of sample and population in quantitative methods and to understand the concept of sampling distribution. We have seen in the earlier modules that descriptive statistics provide information about our immediate group of data. For example, we could calculate the mean and standard deviation of the exam marks for the 100 students, and this could provide valuable information about this group of 100 students. Any group of data like this, which includes all the data you are interested in, is called a population. A population can be small or large as long as it includes all the data you are interested in. For example, if you were interested in the examination marks of 100 students, the 100 students would represent your population. Descriptive statistics are applied to populations, and the properties of populations like the mean or standard deviation are called parameters, as they represent the whole population, that is, everybody you are interested in. Often, however, you do not have access to the whole population you are interested in investigating, but only a limited number of data instead. For example, you might be interested in the examination marks of all the students in India. It is not feasible to measure all examination marks of all the students in the whole of India. So you have to measure a smaller sample of students. Example, 100 students, which are used to represent the larger population of all Indian students. Properties of samples such as the mean or standard deviation are not called parameters now, but statistic. Inferential statistics are techniques that allow us to use these samples to make generalizations about the populations from which the samples are drawn. It is therefore important that the sample accurately represents the population. The process of achieving this is called sampling. Inferential statistics arise out of the fact that sampling naturally incurs sampling error, and thus a sample is not expected to perfectly represent the population. The methods of inferential statistics are: first, the estimation of parameter and the testing of statistical hypothesis. The main objective of this module is to clearly illustrate the main concept of inferential statistics. Inferential statistics is defined as the branch of statistics that is used to make inferences about the characteristics of a population based on sample data. The goal is to go beyond the data and make inferences about population parameters. In order to use inferential statistics, it is assumed that either random selection or random assignment was carried out. That is, some form of randomization must be assumed. Two of the most important basic areas include the understanding of sample and population, while the other includes the concept of sampling distribution. An example of inferential statistics is, if we want to infer the top 5 clothing brands among the youth of Delhi, it would be impossible to take the view of every youth of Delhi and study it. So what do? To solve this problem, we make a sample. That is, we carve out a random sample from the existing population by getting the views and responses from students across 5 or 10 or maybe bigger colleges in Delhi. Then we apply various techniques to get the results. Thus, the results derived from the sample can be used to draw conclusions about the respective population by using methods of inferential statistics. Population and sampling and hypothesis. The population is all the people about whom a researcher wishes to make a statement. The phrase target population is also sometimes used. The hypothesis is a statement about the population and not the sample. A sample is defined as a relatively small set or subset of individuals, group, objects, items and events selected from the respective population. The aim is to select a representative sample from the target population. A small group that represents the target population in terms of characteristics such as age, IQ, social class, relevant experiences and so on. The importance of representativeness is in order to be able to generalize from the sample to the target population. A sample that is not representative is described as biased, that is leading in one direction. A biased sample means that any generalizations lack external validity. Population. A population is defined as the total and complete set of individuals, groups, objects, items and events that the researcher is interested in and is studying them. A population refers to all the data that a researcher is interested in. For example, if we were to study the employment patterns of college graduates from India, our population would include every person who graduated from colleges across India. Sample. A sample is defined as a relatively small set or subset of individuals, groups, objects, items and events selected from the respective population. For example, instead of studying every college graduate across India is difficult and not feasible, which would be a very hectic thing and would cost a lot of time and money, we could select a small sample of recent college students graduated in the last year or so, and then we can study them and then using appropriate methods can generalize the findings to the respective larger population. The aim of all psychological research is to be able to make valid generalizations about behavior. In a research project, only a small number of participants are studied because you could never study the whole population. Psychologists, using sampling techniques which maximize generalizability. Sampling is not limited to participants, and sampling techniques are used in observational studies where term time sampling and event samplings are used. Population parameters and sample statistics. A population parameter is a numerical characteristic of the population, but a sample statistic is numerical characteristic of a sample. Statisticians use Greek letter to symbolize population parameters and English letters to symbolize sample statistics. Some of these symbols are also illustrated in the table. Like mean may be given as x bar as a sample statistic, whereas it is represented as mu by the Greek letter. Similarly, we can see variance, standard deviation, correlation, proportion, regression coefficient are all represented with different symbols for a population and a sample. The diagrammatic representation of population and sample is also given. population leads to a sample selection. The sample gives statistic on application of statistical technique, and of course the sample statistic and population parameters are all there, whereas in inferential statistics we have to estimate population parameters. You can see the population as the larger circle and sample just a small part of it, but retaining all the properties of the population. So from the population you choose a sample by applying sampling techniques. Then we use certain statistical techniques and data collection methods on the sample, and we draw inferences, estimates and conclusions about the population. That of course has its own errors, and then inferential statistical techniques are applied, and we know the amount of error that may also be there. Empirical testing typically involves inferential statistics. This means that an inference will be drawn about some population based on observations of a sample representing that population. This module explains about the procedure of hypothesis testing, including the understanding of null and alternative hypothesis, and statistical significance, which is of utmost importance to explain a research study and its relevance with respect to the population. The module highlights the concept of one-tail and two-tail test used in psychological research, and the different types of errors are also explained, which play a significant role in influencing the results of a particular study. The hypothesis testing. Descriptive research and causal research designs often climax with hypothesis tests. Hypotheses are defined as formal statements of explanations stated in a testable form. Generally, hypotheses should be stated in concrete fashion so that the method of empirical testing seems almost obvious. Types of hypothesis tested commonly include relational hypothesis, that is, how changes in one variable vary with changes in another. Hypothesis about differences between groups, that is, to examine how some variable varies from one group to another group. Or hypothesis about differences from some standard, that is, to examine how some variable differ from preconceived standard. Hypothesis testing is a systematic procedure for deciding whether the results of a research study which examines a sample support a particular theory or practical innovation which applies to the population. Hypothesis testing is a branch of inferential statistics that is concerned with how well the sample data support a null hypothesis and when the null hypothesis can be rejected in favor of the alternative hypothesis. There are various steps which take place in the hypothesis testing process. First is restate the question as a null hypothesis. A research hypothesis, also called alternative hypothesis about the populations. Note that the null hypothesis is usually the prediction that there is no relationship in the population on the chosen variables. The alternative hypothesis is the logical opposite of the null hypothesis and says there is a relationship on the chosen variables in the population. Thus, the null hypothesis is where the means of two populations is same. That is, null hypothesis represented as HO is equal to mu x equal to mu y. That is, the mean of population 1 is equal to the mean of population y and there is no difference. The research hypothesis is that the two population means are not equal to each other. That is, the mean of population 1 is greater than or less than the mean of population 2. The alternative hypothesis is simply stated as mu x not equal to mu y, that is population mean of the mean of population x is not equal to the mean of population y. We are using hypothesis testing when we expect a relationship to be present. In other words, we usually hope to nullify the null hypothesis and tentatively accept the alternative hypothesis. The next step in hypothesis testing, once the hypotheses have been made, is to set the significance level before the research study. Most researchers in psychology use 0.05 as the significance level. Note that the significance level is also represented as alpha level or simply called alpha. The probability value can be obtained using a computer program, or it is also available in the statistical tables. Compare the probability value to the significance level and make the statistical decision. The step 4 includes two decision making rules. A decision made in hypothesis testing centers on the null hypothesis. This means two things in terms of making a decision. First, decisions are made about the null hypothesis. Using the courtroom analogy, a jury decides whether the defendant is guilty or not guilty. The jury does not make a decision of guilty or innocent because the defendant is assumed to be innocent. All evidence presented in a trial is to show that a defiant is guilty. The evidence either shows guilt, decision guilty, or does not, that is, decision is not guilty. In a similar way, the null hypothesis is assumed correct. A researcher conducts a study showing evidence that this assumption is unlikely, then we reject the null hypothesis, or fails to do so, then we retain the null hypothesis. The second is the bias is to do nothing. Using the courtroom analogy again, for the same reason, the courts would rather let the guilty go free than send the innocent to prison. Researchers would rather do nothing, that is, accept previous notion of truth stated by a null hypothesis, than make statements that are not correct. For this reason, we assume the null hypothesis is correct, thereby placing the burden on the researcher to demonstrate that the null hypothesis is not likely to be correct. Rule 1. If probability value is less than or equal to the significance level, that is the alpha value, then reject the null hypothesis and conclude that the research finding is statistically significant. In practice, this usually means if probability value is less than or equal to 0.05, then reject the null hypothesis and conclude that finding is statistically significant. If probability value is greater than the significance level, that is the alpha value, then we fail to reject the null hypothesis and conclude that the research finding is not statistically significant. In practice, if the probability value is greater than 0.05, then fail to reject the null hypothesis and conclude that the research finding is not statistically significant. Interpret the results, that is, making a substantive real world decision and determine the practical significance of the findings. This means that you must decide what the results of your research study actually mean. Statistics are only a tool for determining statistical significance. If you obtain statistical significance, you must now interpret your results in terms of the variables used in your research study. There are 4 decision alternatives regarding the truth and falsity of the decision we make about the null hypothesis. The decision to retain the null hypothesis could be correct. The decision to retain the null hypothesis could be incorrect. The decision to reject the null hypothesis could be correct, and the decision to reject the null hypothesis could be incorrect. When we decide to retain the null hypothesis, we can be correct and incorrect. The correct decision is to retain a true null hypothesis. This decision is called a null result or null finding. Simply putting it, the populations, as we had discussed, if we are finding differences between two populations, have a comparable means, and the difference, if exists between the two populations, is not of significance. So, we retain the null hypothesis. This decision is called a null result or null finding. This is usually an uninteresting decision because the decision is to retain what we already assumed, that the value stated in the null hypothesis is correct. For this reason, null results alone are rarely published in behavioral research. The incorrect decision is to retain a false null hypothesis. This decision is an example of type 2 error or B error. With each test we make, there is always some probability that the decision could be a type 2 error. In this decision, we decide to retain the previous notions of truth that are in fact false. While it's an error, we still did nothing. We retained the null hypothesis. We can always go back and conduct more studies. When we decide to reject the null hypothesis, we can be correct or incorrect. The incorrect decision is to reject a true null hypothesis. This decision is an example of a type 1 error. With each test we make, there is always some probability that our decision is a type 1 error. The researcher who makes this error decides to reject the previous notion of truth that are in fact true. Making this type of error is analogous to finding an innocent person guilty, and to minimize this error, we assume a defendant is innocent when beginning a trial. Similarly, to minimize making a type 1 error, we assume the null hypothesis is true when beginning a hypothesis test. You must also determine the practical significance of your findings. A finding is practically significant when the difference between the means or the size of relationship is big enough, in your opinion, to be of practical use. Effect size indicators are important aids when you are making a judgment about the practical significance. Sampling distribution. One of the most important concepts of inferential statistics is that of the sampling distribution. That's because the use of sampling distribution is what allows us to make probability statements in inferential statistics. A sampling distribution is defined as the theoretical frequency distribution of the values of a statistic that results when all possible random samples of a particular size are drawn from a population. Would be obtained by chance from an infinite number of samples of a particular size drawn from a given population is known as a sampling distribution. Minium and King, 2011. Sampling distribution results from collecting data from a series of observation and then plotting the frequency of each score. It can also be done by taking the samples of a particular size from the population again and again. One specific type of sampling distribution is called the sampling distribution of the mean. If you wanted to generate this distribution through the laborious process of doing it by hand, which you would not need to do in practice, you would randomly select a sample, calculate the mean, and randomly select another sample, calculate the mean, and continue with this process until you have calculated the means for all possible samples. This process will give you a lot of means, and you could construct a line graph to depict your sampling distribution of the mean. The sampling distribution of mean is normally distributed as long as your sample size is about 30 or more for your sampling. Also note that the mean of the sampling distribution of means is equal to the population mean, and that tells you that repeated sampling will, over the long run, produce the correct mean. The spread or variance shows that sample mean will tend to be somewhat different from the true population mean in most particular samples. A sampling distribution can be obtained for any statistic. For example, you could obtain the following sampling distribution: sampling distribution of percentage or proportion, sampling distribution of variance, sampling distribution for the correlations, sampling distribution of the regression coefficient, and sampling distribution of the differences between two means. The standard deviation of a sampling distribution is called the standard error. In other words, the standard error is just a special kind of standard deviation, and you learn what a standard deviation is already in the previous modules. The smaller the standard error, the less the amount of variability present in a sampling distribution. It is important to understand that the researchers do not actually empirically construct sampling distributions. When conducting research, researchers typically select only one sample from the population of interest. They do not collect all possible samples. The computer program used by the researcher uses the appropriate sampling distribution for the researcher. So in the end, we can summarize: inferential statistics undertakes certain statistical methods to determine the difference between the results of a study that are meaningful and those that are merely due to chance variations. A population is the complete set of individuals, items, and events. Hypothesis testing refers to choosing between competing hypotheses about a probability distribution based on observed data from the distribution. Statisticians follow a formal process to determine whether to reject or accept a null hypothesis based on sample data. This process, called hypothesis testing, consists of 4 steps. State the hypothesis. This involves stating the null and alternative hypothesis. The hypotheses are stated in such way that they are mutually exclusive. That is, if one is true, the other must be false. Formulate an analysis plan. The analysis plan describes how to use sample data to evaluate the null hypothesis. The evaluation often focuses around a single test statistic. Analyze sample data, that is, find the value of test statistic, mean score, proportion, t-score, z-score, etc. described in the analysis plan. Interpret the results, apply the decision rules described in the analysis plan, and if the value of the test statistic is unlikely based on the null hypothesis, reject the null hypothesis. A sample is a part of population used for study. Sampling distribution is defined as the theoretical frequency distribution of the values of statistic that results when all possible random samples of a particular size are drawn from the population. It would be obtained by chance from an infinite number of samples of a particular size drawn from a given population is known as a sampling distribution.